For the recording, you have your Expert TA Chapter 12 due on Friday. You have a quiz over the weekend on Chapter 12, and your Explain Something slides are due on Friday as well. Okay, if that makes sense. I think that's all the scheduling stuff we need to talk about. Should we jump into the physics? Excellent. Was there something I was supposed to start, like specific I was supposed to start on, or am I just starting in on Ampere's law?
I don't know. Last thing we left off was on spring.
Oh, okay. We got compressed, right? Yeah. Excellent. Okay. New thought then. This is great. I can start off fresh. We are talking about Ampere's law, which is actually pretty complicated. We're going to find that the math is going to be much better than the math we did on Thursday. However, we're going to find that the concept might be a little denser. And this should remind you a lot of Gauss's law, actually. That over there. So do you guys remember Gauss's law? Maybe, maybe not. It was like 10 weeks ago. It was a long time ago. Really quick, just because it'll probably help us get through this one. Gauss's law was the idea that if you had a closed surface and you put a charge inside of the closed surface, the flux, electric flux, through that surface was directly proportional to how much charge you had inside of it. Sound familiar? And the big idea there was, so this was Gauss's law, that you could set this equal to an equation that included electric field in it. And then you were really clever in your choice of shape, like you choose a sphere or a cylinder or a rectangle. And if you're really clever in that choice of shape that you put around your charge, you could easily do this integral and you could solve for the electric field. So you cleverly chose your area and then you solved for the electric field. Okay, sound good? What we are going to do is we are going to come up with a similar idea for magnetic fields, where we're going to have a current, and we're going to say, okay, I want to be able to talk about that magnetic field in terms of this current. And so what we're going to do is we're going to come up with a clever loop and be able to say something about the current going through that loop with respect to the magnetic field around that loop. And then we'll use that to solve for a magnetic field of various shapes. So here's what I mean. Let's say I have a wire with some current going through it. Now, I know that this wire is going to make a magnetic field around it. But what I might not know is the equation that magnetic field would follow. Like, if I moved further away from the wire, would it depend on how far I am from the wire? Would it be a 1 over r or 1 over r squared? What equation, what sort of equations for this magnetic field could I have? And so what I'm going to find of Ampere's law is, since I know that this wire is going to make a magnetic field, I could make some imaginary loop. Imaginary loop. Not work better on imaginary loop, which is very similar to like Gauss's law, where we like enclose things in imaginary surfaces. So I make this imaginary loop where if I take this loop, which I'm going to call it the loop S, and I'm going to break it up into little bits ds. So I take little bits ds and I dot it with whatever magnetic field that it is on top of, and then I integrate that. So I'm taking this magnetic field, I'm dotting it with each of my ds's as I go around the entire loop, and then I add them up. That'll be equal to the current inside the loop multiplied by some constant. And in this case, the constant we're using is mu naught. Okay, so first off, so let's examine this just by talking about what some like extreme cases. So for example, what if I just made a loop out in space, like over here, with zero current going through it? Would we expect a magnetic field out there? So if I just like here, I have a loop. Should I expect a magnetic field over here? No, right? So I really would only expect a magnetic field if I have some current going through my loop, right? So that's this idea that I need some current going through the loop, and it only matters if the current goes through the loop. It doesn't matter if the current is outside of the loop. Make sense? Okay. And then we have this mu naught. Have we talked about mu naught before? I think I mentioned it. Okay. Okay. So let me go ahead and just write down. So mu naught, permeability of free space. Permeability of free space. You should compare it to epsilon naught, which is the permittivity of free space. Where when we say free space, we mean a vacuum. We mean like a space with literally nothing in it. It is free of any constraints. Where permittivity is how easy or hard it is to get an electric field into a material, in this case a vacuum. Permeability is how easy or hard it is to get a magnetic field into a vacuum in this case, but into whatever material. So various materials have various permeabilities. Permeabilities. For a vacuum, the permeability of a vacuum is 4 pi times 10 to the negative 7th newtons per ampere squared. Excellent. And so while it made sense when you're talking about electric fields, you would have the permittivity of free space running around. Here, when we talk about magnetic fields, we have the permeability of free space in our equations. Okay, so first off, kind of okay on this equation. Let's talk about how this is used. And by that, let's go ahead and look at the long straight current carrying wire again. So say I want long, straight, current carrying wire. So we did this problem last week using the Biot-Savart law, and that was the problem that went on for a while and was not super pleasant. Okay, but now I want to do this again, but I'd like to use Ampere's law. So the thing with Ampere's law is you have to have some idea of what the magnetic field would look like. So just like with Gauss's law, you had to have an idea of what the electric field should look like, otherwise you wouldn't be able to choose a shape well. I need to know how this magnetic field should look like. So I can choose a loop that's just going to kind of lay on top of my magnetic field. So I have this wire, current's going that way. What sort of magnetic field would we expect to see? Okay, yeah, so I expect to see, if my current's going this way, a loop that kind of follows out the path that my fingers, that your right hand is tracing. So I expect to see a magnetic field that kind of looks like that. Okay, and so when I choose my loop, I'm going to choose a loop that just lays right on top of it. And that is because when I do this B dot ds, I want this dot product to be easy. Okay, I don't want to have to figure out, hey, there might be an angle between these two that changes, or maybe some parts of the loop contribute and some don't. If you can lay your loop right on top of your magnetic field, you can easily say, well, B dot ds is really just the magnitude of the magnetic field, the magnitude of ds, and the cosine of 0. Sound okay? Okay. Okay, now looking at this, the other thing that we have done, didn't explicitly say, but we did it, was when we set this loop, we set it at a specific distance away from the wire. Sound okay? So our loop is some distance r from the wire, and we centered it around it. Because we knew that our magnetic field shouldn't be stronger on one side or the other. So we should have a symmetric magnetic field, so we made a symmetric loop of wire, loop of imaginary loop. Okay. Given that our loop is all one constant distance from the wire, this magnetic field, would you expect it to be constant or variable? So the strength of the magnetic field as you go around that loop, would you expect it to change or stay the same? Stay the same. So we can just pull this outside of our integral. We're dropping the cosine of 0 because the cosine of 0 is just 1, right? Okay. And usually when you put a little circle on your integrals, that means that you want to follow it around whatever path you're doing. And the path we're doing is just all around the circle. If I add up all my ds's all the way around this circle, what is the total length of the ds's what should all those ds's add up to? 2 pi r, because they're just the circumference of the circle, right? So this is really b times 2 pi r. Okay, so we started here with this integral of b dot ds, and we've ended up with b times 2 pi r. Now the other half of this rule says you're not just like integrating this, you're setting that equal to mu naught times the current inside the loop. So this is equal to the current inside the loop times this magnetic permeability, which brings us to the magnetic field of that wire is mu naught I over 2 pi r. Whoosh. And if you look back in your notes, that's what we got to with the Biot-Savart law after a page or 3 of calculus. Did that kind of make sense? I hope so. I hope so. Long straight wired. So this Biot-Savart law, it is just like another way to figure out an equation for a magnetic field of some given setup. The pros are that mathematically it tends to be pretty simple. The cons are you really have to know exactly what your magnetic field is going to look like before you start work on this. Does that make sense? So conceptually a little harder to set up, mathematically much easier. And if that made sense to everyone, let's do another shape. The next shape I want to do is a weird one. It's a toroid. Where a toroid is a donut. So you have your toroid is usually there's like an iron core, something like that. And then you have looped wire around it. So you have like a wire coming in that goes around like that. So current in, current out. Okay, can you kind of picture this? It's just like the electromagnet you made in lab last week, but then you curled it in a circle. So if my current's going this way, it's going down like that. Okay. I would like to find the magnetic field inside that where it's looped around. And we're going to use Ampere's law to do this. But before we do that, we have to kind of think about what the magnetic field is going to look like. So let's do this kind of step by step. Let's look at this guy right there. Okay, if you just had that one little loop of wire, which way would the magnetic field go inside of that loop of wire? I like it. So you curled your fingers around and your thumb is going like that, right? Okay, let's go to the next little loop of wire. This guy. Which way is the magnetic field from that loop of wire? Curl your fingers in the direction of the loop. So now the current's going around like this. So you curl your fingers, there we go, and your thumb should be pointed. Oh, you're backwards for me. That's why this is confusing, right? Sorry, this way. So yeah, I'm still mirror imaging here, like that. And as you go around, you guys should see that each one kind of is lining up, right? And so the idea here is I did actually draw these kind of spaced out, but usually you have them pretty tightly together. So as the magnetic field starts going, it has to go around in that loop. Magnetic fields are kind of weird because unlike electric fields, they don't begin or end, they just loop. And so they can't just end somewhere. You can guide them. So if you have a magnetic field and a magnetic field and a magnetic field, instead of just like stopping, they'll make a loop however they can. Does that make sense? You can make weird shapes with magnetic fields. That's like an entire industry, making weird magnetic fields. Okay, but with that, now we have a pretty good idea of what this magnetic field should look like. It should be looping around in this circle. Given that we have this circle, that means I should probably give us a radius like that. And so let's go ahead. So my magnetic field's in green. Let's go ahead and lay down our imaginary loop. And we just lay it down right on top of our magnetic field. So our imaginary loop just lays right on top. Okay, so B dot ds equals mu naught I. Now, mu naught I, and let me say like I inside. Okay. This, let's do the dot product first. So my DS's are going around along the red line. My magnetic field is the green line. What's the angle between the green line and the red line? Let me see a good zero here. Yeah, they're in the same direction. Like, does it ever change? So like, if you look at one spot, they're pointing in the same direction. As they go around, are they always in the same direction? Okay, so we can go ahead and say this dot product is giving us just BDS times the cosine is 0, but that's just 1. And then we're going to say, okay, do we expect the strength of the magnetic field to change as you go around that circle? Is there a physical reason why it would be stronger on one side than the other? I like, no. Now I do have to put in like a few caveats here, because if I had wound this magnet weirdly where I had like more loops on one side than the other, like that would be a reason. And I tried to draw these evenly spread out, and you would evenly wrap it around the whole thing. So as long as I've done this in a very symmetric sort of way, and also if you look at where I have the current coming in and the current coming out, those should be pretty close to each other as well. But as long as I've wound this carefully, my magnetic field should be constant throughout that circle. So we're going to take that outside, and we're integrating this ds over my loop. Okay. Looking at this, I have my loop. I'm integrating over ds. Once again, if this is a circle radius r, and I add up all my ds's, what am I going to get? 2 pi r? 2 pi r. Excellent. Okay, I have 2 pi r on that side. All right, so I have one side of this equation. Let's look at the other side, where the other side, we look at all the current going inside of that red circle. Okay, it doesn't matter what's going on the outside of the circle, only the inside of the circle. Looking at this picture I've drawn, if I have, let's just say I have current I in this wire, how much current do I have going through the circle? And what do you think I might be talking about? Let me ask you a question. If I had more loops of wire, would you expect the magnetic field to be stronger or weaker, or does it depend? Stronger. Okay, so the more loops of wire, the stronger the field. So I need to account for the number of loops of wire I have, right? And if you look at this, I have current going into the circle once, twice, 3 times, 4, 5, and 6. So 6 times that wire goes in through my circle. And so I have 6I going into the circle. 6I. Does that make sense? And we're going to generalize this. I'm going to say you have n loops. So n is the number of loops. Which, by the way, sometimes you say turns instead of loops. If you ever hear that. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. I did that right. Okay, so I have n loops. So on the other side of this, B times 2 pi r equals mu naught Ni, or my magnetic field equals the permeability of free space, the number of loops on my toroid, the current in my wire, divided by 2 pi r, which is the circumference of my circle. Everyone kind of okay with that? Awesome. Okay, I think I only have one more shape to go. So far, you guys happy? Okay, because the one more shape I have to go is a really popular shape, solenoids. Have you guys ever heard of solenoids before? Really? Okay, there's one in your car. There's several in your cars. But a solenoid is just a cylinder of wire, like so. Usually very tightly wrapped. And this is definitely the shape that you use if you want a magnetic field. So you know how, well, let's look at the magnetic field, and then you will see. So I have current going in, I have current coming out. So there's my current as I'm going around this cylinder. Which way is my magnetic field? Yeah, it's going upwards through here. And we're going to find that it's not only very strong on the inside of the solenoid, it is very consistent on the inside of the solenoid. So yeah, we're going to find a really consistent magnetic field that does this. And so the solenoid is kind of like the magnetic analog of a capacitor, of a parallel plate capacitor, where we talked about parallel plate capacitors a lot because they made this region of constant electric field. And we liked a nice, simple, constant electric field. Solenoid is going to give us the same thing. It's going to give us this nice region of constant magnetic field. And so most of the times when you see electromagnets being wrapped, they're wrapped in a solenoid-y sort of fashion. Okay, but of course what we want to do is we want to figure out the magnetic field of a solenoid. And so there's a few things here. One, you notice that I didn't draw this in a loop. And let's talk about why. So because it is in a loop, but it's kind of a weird one. So if I just wanted to talk about like bits of wire. So like each of these loops of wire, I have current going into the page on one side, and I have current coming out of the page on the other. So like here's my current going into the page, my current coming out of the page. Sound okay? Each one of those wires wants to make a magnetic field like that. This one is going this way. And this one is going this way. Right? But what happens is that when they start to overlap, kind of the same thing that was going on in the toroid, they start to add together, and so they're trying to make some sort of loop. And so instead of something like this, they start to kind of form loops like this that go around like that. And the same thing, of course, on the opposite side. I do this one backwards, guys. Do this one backwards? Yes, I did. Let me just make sure I have all my magnetic fields pointing in the right direction. And this one comes this way. Okay, much better, much better. Sorry. Where you idealize it as magnetic fields that do that. And so I'm kind of hoping that you see that this really starts to look very much like a bar magnet with a north side and a south side. Where on the inside, the field goes from south to north, and on the outside, the field goes from north to south. And maybe you looked at this in lab last week. Maybe you might remember wrapping an electromagnet and then saying, hey, there's a north side to this electromagnet and a south side to this electromagnet, just like you would a bar magnet. Okay. Everyone pretty good? All right. So what this gives us is this gives us a shape to work with. And so let's talk about the shape that we need to have. We are going to want to just lay our loop down right on top of one of these, but we're actually going to say something very physicistly. We're going to say an infinitely long solenoid. And you might ask, why would you want an infinitely long solenoid? And I would tell you that if this solenoid is infinitely long, that it goes on forever, can this magnetic field ever get out of my solenoid? No, I have trapped it inside my solenoid. And so that's going to be kind of a key thing here. We're going to say I have an infinitely long solenoid. It's going to trap this magnetic field. On top of that, I'm going to want to talk about a magnetic field per unit length of my solenoid. So I'm not going to have a loop that goes around this entire thing. I'm going to just take a chunk out of it. And so let's start constructing my solenoid. So I'm going to draw this as just the outside wires. So we can just look at the outside wires. So I have one side of it where the wires carry the current into the page. The other side, the wires are carrying the current out of the page. Is my magnetic field inside the solenoid going to the top of the page or the bottom of the page? So I have, so what's happening is the current's coming out and then in. Another way to look at it is take just one of these. Point your thumb in the direction of that current. So like that guy over there, curl your fingers around. And so on the inside, you expect the magnetic field to be going down. Does that make sense? So like if I just took one of these, it's making a magnetic field like this. And so that means my magnetic field is going to be going down on the inside. Okay. And then on top of that, I'm going to put my loop like that. It's going to be L long, it's going to be W wide. And I'm gonna label, I have sides 1, 2, 3, and 4. Sound good? Okay. Let's start filling this in. So we have B dot ds equals mu naught I inside. And let's look at this B dot ds because we're going to break it into 4 groups. We're going to go along 1, then 2, then 3, and then 4. Okay. And let's take care of 2 and 4 really quick. When I take the dot product, so let's start with 2. My DS's are just small chunks of that line. My magnetic field, if it encounters it, is going that way. What is the dot product between those DS's and the magnetic field? What's the angle between those DS's and the magnetic field? 90, and what is the cosine of 90? 0. And so the dot product between the magnetic field and those DS's is 0 because they're going in completely opposite directions. So this guy over here is 0. What about side 4 on the top? If I do a B dot ds for the top side of this rectangle, also 0. Excellent. Okay, that makes this easier. Now let's deal with number 3. And this is a shaky one. And we're going to speak about this as we go on. I have an infinitely long solenoid. You guys told me the magnetic field couldn't get out, right? Like when I drew this line right here, what that meant was this magnetic field had to bend. It couldn't get out. So what should the magnetic field on the outside of my solenoid be? You want to say 0, right? And you would be right to say 0. And so here's what's kind of interesting about this. This is true. And I don't know, I've never come up with a perfect explanation of this because my mind doesn't like it. But it's true. If you look on the outside of a solenoid, you'll see little to no magnetic field. And if you make sure your solenoid is long enough compared to where you look. So like if you look right here, if you try to measure at this point here, you'll find like that's pretty close to 0. If you get nearer to an edge, that point, you don't have 0 anymore. You're going to see that edge effect. If you go too far away from it, like over here, again, you're not going to see 0. It's not going to be very strong, but it's not going to be 0. Because the idea is the closer you get to this, your perspective changes so it looks longer. Does that make sense? Like if you're really close to something, you might not be able to have the same perspective on it. And so even with a non-infinite solenoid, as long as you stay relatively close to that edge, your magnetic field will be close to 0. It's only when you get far enough away or close enough to the edge where you start seeing the edge effects where the field's leaking out, that's when you're going to start seeing a magnetic field on the outside of your solenoid. Sound okay? And it works. It's pretty sweet that it actually works too. Okay, that means that, okay, so like this B goes to 0. That means that this integral is really, we're just looking at side 1, the one inside the solenoid. And so now when I'm doing my B dot ds, my DS's are going like that. My B fields going like that. There's a 0 angle between my B field and my DS, so I get that cosine of 0, that's just 1, right? So this becomes a very reasonable BDS. And then you're going to tell me that all along side 1, my magnetic field should be constant. It shouldn't be stronger on one side or another, because this is a really symmetric situation. It doesn't change. So I can say B integral of ds. Okay, and if I'm integrating ds over length L, so I add up all my ds's, they should add up to the length L, right? Okay, so I have B times L. So that's one side of my Ampere's law. Next thing I need to do is I need to calculate how much current is going through my loop. And let me tell you, this is a wire, right? And it's got current I going in it. In my loop, those are how many wires go through it. So I have 1, 2, 3 I. But if I lengthen it, it would just be however many number of turns I have going through my loop, right? So I'm going to say on the next page here that I have, on one side I have B times L, on the other side I have mu naught times the number of turns in my loop times the current in my wire. And then there's a few things we're going to do with this. I'm going to divide both sides by that L, and I'm putting this N over L together, where capital N is the number of total turns in my solenoid. So if I wrap that wire around a solenoid 100 times, I have 100, N is 100. But we're going to introduce lowercase n, which is we're going to call the turn density, which is the total number of loops per unit length. We call that turn density. where if I have, what, 10 loops per 10 loops per centimeter, that would be a lowercase n. So I might have 100 loops total, but for every centimeter, I might only have 10 loops. Sound reasonable? Okay. And so you see this becomes mu naught Ni. And that's usually how you see this written. Magnetic field, the field of a solenoid. Field of solenoid. Okay, few things. This magnetic field, does it have any variables in it? For example, I have my solenoid. Let me clean up this picture a whole lot. I have my solenoid here. I'm talking about this magnetic field inside of my solenoid, my B. I say it's equal to mu naught Ni. If I'm looking at this region versus this region, would I change? No, right? Because it's the same wire, so it should have the same current. How about my turn density, loops per unit length? No, right? I have responsibly wound this magnet. It's a good magnet. Permeability of free space, definitely a constant. So whether you're up at the top or down at the bottom, your magnetic field is the same. What about if you're at the right versus at the left? Would any of these things change? No, right? There's nothing in here that says you need to be so far away from the wire, as opposed to like my other equations that have some sort of distance in them, right? That's kind of a weird, yeah, that have some sort of distance. Talk about whether you're close or far away from the wire. This guy does not. So when I was saying how that magnetic field is constant throughout the solenoid, this is what I was talking about. It is constant. As long as you're inside the solenoid, it's the same. So if you need a region of constant magnetic field, this is how you make it. Reasonable? Okay, okay. So what else do I need to tell you about solenoids? Probably that's it. They're very cool. They do a lot of things. Probably that's it. I feel like I'm forgetting something, but don't. I'll remember before we. I'll remember by next class at least. However, if we're all good there, shall we do a problem or two? The problem that I really wanted to do is I really wanted to do number 16 before we stopped this chapter, because that one's kind of a rough problem. Yeah, let's do that one, and then if you guys have anything else, I'd be happy to do it maybe on Thursday. But number 16. I want to do number 16 because you have to be kind of careful setting up this problem. Where I have a long straight wire with a current in it, and I have a region of space over here that is a distance c from my wire, and width a, length b. And I'm going to set up my coordinate system so I can talk about some distances from the wire r. So when I talk about r equals 0, starts at the wire, points out. I would like to find an equation for the magnetic field in this region. Sound reasonable? And at this point, we would just look that up, right? because we have found this equation two different ways. Okay. B field of a long straight current carrying wire, mu naught I over 2 pi r. I got to tell you, I can never keep all these equations straight, so I highly recommend like having a cheat sheet or always looking them up, because like I say, I can't keep them straight. They're all really similar. But that's the one for the long straight wire. Okay. And then the reason I wanted to do this one is the next thing it asks for is a magnetic flux. And we haven't dealt with that yet. And next chapter, it's going to become very important. So I would definitely like to introduce this concept. It will be really similar to electric flux, where if I needed to talk about the electric flux through some surface, I would take the electric field and dot it with the area. Now, if my electric field was constant, I could just say E dot A. But if my electric field was not constant, I had to chunk my area up into little dAs, find the flux through each one, and then add them all up. Magnetic flux, just the same, where magnetic flux, if it's not constant, you take the magnetic field, dot it with the area, and then add up all your little areas. If your magnetic field is constant, you can just take your entire magnetic field, dot it with your entire area, and you'll be done. Any questions about this? Does this seem like a reasonable concept? Okay, we're going to talk about it a whole lot on Thursday, but just as a general idea, you take your field, you dot it with your area. Okay, so now I need an equation for the magnetic flux through this region. Is my magnetic flux through this entire rectangular region, is my magnetic field through this entire region the same? So if I chose two spots here, would my magnetic field be the same or would it be different? Say I chose this spot here versus that spot there. Would I have the same magnetic field at both spots, or would they be different? Say different, right? Because my magnetic field depends on how far I am from the wire. Okay. What if I had a spot here versus a spot there, where they're kind of along the same line? Would the field there be the same or different? The same. Okay. So when I'm looking at these areas, I'm definitely going to have to chunk this up, but it would probably be convenient to chunk it into strips here. Make sense? Okay. This looks good. Okay, so I have that's how I'm going to chunk it up. I'm going to chunk it up into dAs, like that, where each of my strips there is going to be some distance r from my wire. And in fact, we could say this has width dr. Makes sense? And if each chunk has width dr, could we express dA in terms of something else, maybe that I've written down here? Like, what's the area of that strip in terms of dr and b, perhaps? dr times b, right? Because it's just a rectangle. So b dr. Okay, that's looking pretty good. Let's put it together and see how much more we have to deal with this. So I'm gonna take this equation. I'm gonna plug in my magnetic field, and I'm gonna plug in my dA. Okay, so I have this flux B. I'm integrating over this total area. My magnetic field is mu naught I over 2 pi r. And we're going to dot this with B dr. Okay. Let's deal with this dot product next. That's what needs to happen next. What direction is the magnetic field in my rectangular region? Like it into the page. Okay, so I expect to see a magnetic field into the page here. What are the two directions my area vector could be in? Could it be towards the top of the page? If I have like a rectangular region here, into the page, yeah, it has to be perpendicular to my surface, right? And since it'd be easier for me not to deal with a minus sign, let's put my area vector into the page as well. Okay, and if they're in the same direction, that means my magnetic field and my dA line up, and the angle between them is 0, and the cosine of 0 is 1, and I can just ignore that dot product. Okay, so this will just equal mu naught I 2 pi r b dr. Okay, this is going to come together. Let's start pulling out constants. What constants do I have inside this integral? Mu naught. I like I. 2 pi. B. Excellent. And so the only thing I have left is I have this dr over r. Okay, we can integrate that. What's the integral of dr over r? Dx over x. Does that make you happier? Natural log, you got it. Okay, excellent. So we have the natural log. Okay, but of course we need to put in limits to this integral. So r starts at the wire and goes out. We're integrating all of these little drs. So we're integrating a whole bunch of little drs here. Where should we start adding up drs and where should we end? C, start at C, end at C plus A, perfect. So we want to start at C, we want to end at C plus A. That looks pretty good. Okay, yeah. So I have mu naught I B over 2 pi, natural log of C plus A minus the natural log of C. We, of course, are going to say the natural log of A minus the natural log of B is the natural log of A over B. And we are going to arrive at a very nice mu naught I B over 2 pi natural log of C plus A over C. Okay, I'm quite happy with that. Yeah, I'm quite happy with that. Did that make sense? Okay. I need to continue that problem in a day or two when we start going. But let's remember that one. All right, but now at this point, I'm coming to the end of chapter 12. Are there any other homework problems that you guys want to look at from chapter 12? You guys are confident? Okay. Okay, I'm gonna go ahead and let me just like start chapter 11 or 13, whatever chapter we're on. Let me just start it. I have like 8 minutes. I can start something. Because this might be the best chapter. This might be the best chapter. This chapter, we're looking at Faraday's law of induction. Okay, so far we have done electrostatics, which is what do electric charges do when they're not moving? They make electric fields. Then we started with electrodynamics, which is, okay, I'm going to start moving charges. What do they do? And so we got that electric charges make electric fields. And then we got this idea that if you move your electric charge, it makes magnetic fields. So far we have that electricity can make magnetism. Now we're going to flip it around. Now we're going to talk about how magnetic fields can make electric fields. So this is where we've got it one way. Now we're really going to start seeing how electricity and magnetism really are the same thing. So what Faraday's law of induction says is it has this idea of change. Because you notice your electric charges, they didn't make magnetic fields until they started moving. So things needed to change to see those magnetic fields. Faraday's law of induction has the same idea, where you can't just make an electric field with a constant magnetic field. You have to change your magnetic field. In particular, though, you have to change a magnetic flux. So, okay, so this is Faraday's law. Faraday's law. And so let's look to this. This is an EMF. So that's like a voltage. We're going to relate it to electric fields in a little bit. But very, very electrical concept. Over here, I have this magnetic flux, which we have just been calculating, where your magnetic flux, B dot A, or you, of course, can have this be an integral of B dot dA. Okay, so what this says is that if you change the magnetic flux through some region, some area, that will make an electrical voltage. Let's talk about that some more. So that'll make an electrical voltage that not only will respond to this change, but it'll respond trying to stop the change. And so you see this minus sign. Tries to stop change. So anytime you have a flux that changes, a voltage will show up that will try to oppose that change. And it does this through Lenz's law. Lenz's law, which says that if you have a voltage that shows up in one of these Faraday's law sort of situations, if possible, the surrounding materials, the materials involved, will use that voltage, that Faraday's voltage, magnetic field. And that magnetic field will try to stop the change. Okay, so say, for example, you had a situation like this, where you had your loop of wire. You had, let's say, a loop of wire that defined that region of space. If I took that loop of wire and moved it further away from the wire, my loop, and moved it further away from my long straight wire, what would happen to the magnetic flux through my loop? Would my, so I have my loop and I have my long straight wire. I'm going to take this loop and I'm going to move it away. What would happen to the magnetic field that it was experiencing? I like the decrease, right? Because now it's further away from the wire. I see less field. So if my magnetic field decreases, my magnetic flux will decrease. Okay, what would happen then is, as this guy moves away, it sees this magnetic flux decrease. It will have a voltage on top of it. It'll act like there would be a battery put in it to try to oppose that change. And if it's an actual loop of wire, it can support a current, right? It can do a V equals IR sort of thing. And so if it has the V, it'll try to make a current that will create a magnetic field. So for example, if this loop is moving away, it sees a magnetic field into the board, and then it sees less magnetic field into the board. It will want to make more magnetic field into the board. Does that make sense? So it will see less magnetic field, so it'll want to make a magnetic field like that. And so to do that, it will create a current going like that, that will stop the change that it saw. Does that make sense? And I need to stop talking now. And I will say a whole lot more later. There's more to this, but the idea is that this Faraday's law can create electricity to try to stop things from changing. Okay. Online people, are you doing okay? I swear I opened this chat earlier. Oh, 18? I'm sorry. I swear I did open that chat. Can you remind me to start with that on Thursday? We can go ahead and start with that and then jump into a whole lot of Faraday's law stuff. Okay, thank you. And I will see you guys on Thursday.